Hello my Whoop friends. This video is part of a short video series where I try to share my experiences with the Meteor 75 Pro with you, as well as all my Whoop knowledge. I'll try to show you valuable tips and tricks that should help you with the Meteor 75 Pro Whoop as well as with other tiny whoops. Check out the other videos on my channel to get the most out of my many years of whoop race and RC flying experience. Let's get started.
Hello my Whoop friends. This video is about how you can build your own 5.8 gigahertz or 2.4 gigahertz antenna. It's going to be a short video and I won't go deep into the subject this time. I hope that some antenna experts in the comments can help answer any more in-depth questions you might have. I'm not an antenna expert myself and I don't need to be because I usually fly my Whoop alone at a playground, often at distances under 50 meters. For my needs, a simple linear monopole antenna is usually enough, or a T or Y dipole antenna like the ones you can see in this video. The stock omnidirectional polarized antennas with the protective cap, which come pre-installed on many VTXs and Whoops, are also okay, but at 0.5 grams, they're a bit heavy for Whoops. And the circular polarized dipole antennas, which weigh over a gram, are clearly too heavy for a high-performance Whoop, except for the tiny Whoop small antenna. In terms of durability and crash resistance, the simple antennas are also much better. That's why, for me, only the T or Y dipole antennas remain as realistic options for improved performance compared to a linear monopole antenna. Everything else, in my view, is not suitable for Whoop racing due to the weight, size, and lack of crash resistance. Of course, everyone can decide for themselves what's most important to them. For some people, a 1-gram antenna is no problem. But for me personally, only the small, lightweight, and sturdy antennas are an option. I don't want to bother with anything else anymore. If you can benefit from this video and would like to support my work financially, you can now easily do so with a PayPal donation at www.ko-fi.com/ButterflyFPV. Thanks for the support, my Whoop friends. Of course, I'm still happy to receive your comments. Now, back to the video. The connection of a dipole antenna, or a monopole antenna with shielding, to the flight controller or video transmitter is nowadays usually done using an IPEX connector, which is also sometimes called IPEX1, IPX1, MHF1, or UFL connector. At this point, it's important to know that, according to the manufacturer, the IPEX connector on the antenna is only rated for 10 mating cycles. After that, the performance of the connection begins to degrade. The second way to connect an antenna is by soldering it directly to the antenna solder pads on the flight controller or video transmitter. Dipole antennas typically have 2 or 3 solder pads, 1 or 2 ground minus pads for the shielding, or one pole of the antenna, and 1 pad for the other pole, which I'll refer to as the plus pole. The same applies to monopole antennas with shielding. Simple monopole antennas without shielding only have 1 solder connection. These basic antennas can be soldered directly to the antenna's plus pad or to the center pin of the IPEX connector. Of course, after doing that, the connector can no longer be used for its original purpose. In the FPV hobby, antenna radiation patterns can be divided into 3 main types. The first radiation pattern type is omnidirectional, meaning the radiation pattern has a donut or bagel shape. The radiation is almost evenly distributed around the antenna, with the exception of the top and bottom, where there is virtually no radiation. These omnidirectional antennas have a low gain value. The radiation spreads equally in nearly all directions, but it's not very strong. Omnidirectional antennas are ideal for objects that are constantly moving, like our FPV drones. That's why our antennas, such as the simple dipole antenna, often used by manufacturers as the standard stock antenna, mushroom or cloverleaf antennas, and T-Style or Y-Style antennas, feature an omnidirectional radiation pattern. The second type of radiation pattern is directional antennas with medium gain, which emit more radiation toward the front of the antenna. These antennas are suitable for use as receiver antennas on FPV goggles during flights that require more range, while still providing a certain degree of lateral coverage. Directional antennas with medium gain are a good compromise for medium-range flights. The third radiation pattern type is directional antennas with high gain, intended for long-range flights where strong radiation in a single direction is needed. You can imagine this like a flashlight beam, narrow but reaching far. Antenna polarization refers to the orientation in which the electromagnetic wave is transmitted or received by the antenna. In the FPV hobby, we mainly use two types of polarization, linear and circular. With linear polarization, the electromagnetic wave has a planar form. A plane electromagnetic wave is characterized by electric and magnetic fields traveling in a single direction, without variation in the two orthogonal directions. The electric and magnetic fields are perpendicular to each other and to the direction of wave propagation. I won't go deeper into this topic here because it's not necessary. If you'd like to learn more, please refer to the links in the video description. What's really important to know is that linearly polarized antennas have a higher cross-polarization loss compared to circularly polarized antennas. In other words, they are more sensitive to the orientation of the antenna than circularly polarized ones. I'll talk more about antenna orientation later in this video. Theoretically, this makes linearly polarized antennas less suitable for drones. In practice, however, linearly polarized antennas are still commonly used on tiny whoops, mainly for reasons of space, weight, cost, and durability. On the video receiver side, though, circularly polarized antennas are often used. The second type of polarization is circular polarization. In this case, the electromagnetic wave that leaves or is received by the antenna takes the form of a spiral, which can rotate either clockwise or counterclockwise. If the field rotates counterclockwise, it is referred to as right-hand circularly polarized, RHCP. If it rotates clockwise, it is left-hand circularly polarized, LHCP. It is important that you do not mix the different polarization directions with each other. It is not impossible to fly with mixed polarization directions, but it is not optimal. So you should either use RHCP antennas or LHCP antennas. The reason for the different polarization directions is a reduced susceptibility to interference of the signal when you fly together with other FPV pilots. In this case, for example, the pilot on channel R1 could fly with RHCP, the pilot on channel R2 with LHCP, and the pilot on channel R3 with RHCP, and so on. But this is quite impractical if you constantly have to change the channel at a drone race. You would then always have to bring an RHCP drone and an identical LHCP drone so that you don't always have to change the antennas. What's really important to know is that circularly polarized antennas have a lower cross-polarization loss than linearly polarized antennas. In other words, they are less sensitive to antenna orientation compared to linearly polarized ones. I'll talk more about antenna orientation later in this video. Theoretically, this makes circularly polarized antennas the best choice for drones. In practice, however, linearly polarized antennas are still mostly used on tiny whoops, mainly for reasons of space, weight, cost, and durability. On the video receiver side, though, circularly polarized antennas are often used. To achieve circular polarization, the following criteria must be met. The E field must have two orthogonal perpendicular components. These components must be 90 degrees out of phase. The E field's orthogonal components must have equal magnitude. Again, I won't go into more detail here since it's not necessary. If you want more in-depth information, check out the links in the video description. Regarding the topic of polarization, it is important that you know that the optimal pairing and alignment of the transmitting antenna and the receiving antenna is horizontally linear polarized to horizontally linear polarized, or vertically linear polarized to vertically linear polarized. Or horizontally circular polarized to horizontally circular polarized, and vertically circular polarized to vertically circular polarized. However, with tiny whoops, this can practically never be permanently achieved in practice. because the antenna on the drone is always moving through space while flying. And even the ideal pairing, circular to circular and linear to linear, is rarely found with tiny whoops, especially because circular polarized antennas are often too heavy for high-performance racing tiny whoops. That's why I show you in this video how you can make your own linear T-style or Y-style dipole antennas, which are a good compromise between weight, transmission power, and durability. On the video receiver module on the goggles, most tiny whoop racing pilots use circular polarized omnidirectional antennas for good reception in all directions in the close range area. But these omnidirectional antennas have a weak spot above and below the antenna, as you have now learned. That's why on my goggles and my rapid fire diversity module, I have mounted one antenna in horizontal orientation and another omnidirectional antenna in vertical orientation. This way I have a spherical reception coverage in all directions. Ideally, the antennas should be mounted with an extension so they are above my head when I'm flying. But since I always fly in front of me and not behind me, I prefer to have the antennas directly on the goggles because it is more practical for transporting the goggles. As you can see, it is important that you choose your antennas according to their intended use, and that you roughly know and understand the radiation pattern of your antennas. A small stumbling block is also moving your head. Many pilots move their heads while flying FPV, which is of course not ideal for the alignment of the antennas. This becomes even more important with directional medium or high gain antennas, also called patch antennas. So if you tilt your head a lot while flying FPV, then either bend the antennas into a position where the alignment is correct even when your head is tilted. Or even better, learn to stop moving your head while flying FPV. That is better for your back and better for the alignment of your antennas, and therefore also better for your video quality. Attention, my whoop friends. Never fly without an antenna on the video transmitter. This applies to other transmitters as well. If the transmitter is powered on but no antenna is connected, all the energy is reflected back into the transmitter's electronics, heats it up, and causes damage. At 25 milliwatts, the VTX usually survives, but with higher milliwatt levels, the VTX can be quickly destroyed. So always make sure an antenna is connected. On the receiver, it's not as serious if there's no antenna, but on the transmitter, the antenna is a must. The length of the active part of 5.8 GHz antennas for FPV ranges between 11 millimeters and 13 millimeters. For the antennas I measured for this video, the active part was approximately 11 millimeters in each case. The shorter the active part of the antenna, the more it is optimized for the lower frequency range of the 5.8 GHz band. And the longer the active part, the more the antenna is optimized for the upper frequency range of the 5.8 GHz band. In theory, each frequency has an optimal antenna length, but other factors also play a role, such as the length of the shielding, the material of the shielding, the cross-section and material of the antenna, and whether or not the antenna is covered with heat shrink tubing. Additionally, the structure and quality of the video transmitter electronics also matter, and how well they harmonize with the antenna. This is probably also the reason why simple linear dipole antennas come in such different dimensions, as you can see in the photos in this video. On top of that, many VTXs have quality issues or are poorly designed. For example, in the first beta FPV 5-in-1 boards with the 25 milliwatt setting, the VTX was outputting almost 200 milliwatts on channel R1 and only 28 milliwatts on channel R8, according to Chris Rosser's video. If you test an antenna on channel R1 with such a VTX, and then for some reason fly on channel 8 when testing another antenna, it creates the illusion that the first antenna was much better, which, of course, would be complete nonsense in this case. There are really many pitfalls when it comes to building and testing antennas. According to Chris Rosser, many VTXs tend to output more power on the lower channels. Therefore, it would probably make sense to make self-built antennas a bit too long rather than too short, so that they are optimized for the higher channels, which often transmit more weakly. That way, in theory, you could achieve more consistent video quality across all channels. Building an antenna that works reasonably well is easy. But to truly optimize an antenna, you have to deeply engage with the topic, consider all factors, and have the ability to measure prototype antennas with high-quality measuring equipment. I hope I was able to show you that when it comes to antennas, It makes sense to either go all in or otherwise work by the motto, close enough is good enough, and also that you should just experiment. In my opinion, for hobby antenna builders, all that's left is hoping, praying, and trying things out. Everything else is an illusion. To go beyond that, you need a lot of knowledge, high-end measuring tools, and time. As a general rule, circularly polarized antennas are the way to go if you want maximum image quality. Linear dipole antennas are a compromise, and monopole antennas are the lightest option for maximum tiny whoop flight performance. Don't expect a perfect DIY antenna, my whoop friends. As you've now learned, building an above-average antenna is quite difficult and really a job for professionals. So don't expect your self-built antenna to outperform a store-bought one. It's definitely possible, but as an amateur antenna builder, it's probably just luck if that happens. And often you won't know exactly why the DIY antenna is better or worse, and you won't be able to reproduce the result. That's why you shouldn't expect a perfect DIY antenna. The antenna will work. That's all you can reasonably expect. And even if the DIY antenna works well when you fly alone, that doesn't necessarily mean it will perform well when flying with other pilots. It's possible that your antenna VTX combo is spreading signal across multiple frequencies and interfering with the video signals of other pilots. Signal scattering across different channels is a serious problem when flying with others. Sometimes, video reception gets slightly worse after a hard crash. The most common cause is that the UFL connector of the antenna is not fully plugged in anymore. Simply reattaching it properly can often fix the issue. In some cases, however, the IPEX connector on the VTX side is torn off, which is not so easily repairable, especially if the solder pads are ripped off, which unfortunately does happen, particularly if the antenna wasn't intelligently mounted in the tiny whoop. For longer antennas, using a strain relief with dental floss or another thread can help to prevent pulling force on the UFL connector. In some cases, the antenna itself is damaged and needs to be repaired or replaced. That's why it's always a good idea to have at least one identical spare antenna at home so you can swap it out and check whether the antenna is the source of the issue. Unfortunately, it's also quite common that the VTX electronics themselves are damaged. The VTX may still transmit a video signal, but of poorer quality than before the crash. I've experienced this several times. In that case, repair is usually no longer possible for a non-professional, and you'll need to replace the VTX or get a new flight controller. If the screen is gray, the problem lies with the camera, not the VTX. And if the on-screen display disappears, then the issue is with the flight controller. If you experience video interference when flying with other pilots, it's important to make sure that all pilots have their transmission power set to 25 milliwatts. Just asking them is often not enough. Make sure they actually show and prove to you that their output is set to 25 milliwatts. Another important point is the distance to the racetrack. Pilots should maintain a minimum distance of 10 meters or more from the track, and even more importantly, from the start and landing area. It's also crucial that pilots only power on their drones at the start and landing spot. Also note, antennas with high gain are not an advantage when flying with others. High gain antennas pick up interference signals more easily too, so identifying the source of interference is important. This is often due to poor quality or defective video transmitters. As mentioned before, antenna quality and the VTX antenna combination also play a role. As you can see, it's all quite complex. To test your RF environment before a flight, or to test a VTX, you can use the spectrum analyzer in your goggles video receiver module. Most modern high-quality video receiver modules come with a basic spectrum analyzer. With it, you can see which frequencies have interference. When all drones are powered off, there should be no peaks visible on the spectrum. If there are, the interference might be coming from Wi-Fi or other sources, in which case it's important to use free, unoccupied frequencies. If your video receiver module doesn't have a spectrum analyzer, you can simply observe the image in your goggles while cycling through the channels. Even snowy static, called white noise, indicates a free frequency. As soon as you see lines or other types of interference on a channel, that channel is likely being affected by something. Maybe I'll do a more in-depth video on this topic at some point. When mounting your antenna, make sure it can't get caught in the propellers, for example, by creating a small antenna holder using zip ties. Make sure the antenna is securely fixed in place. For longer antennas, I recommend adding a strain relief using dental floss or another kind of thread. That way, if the antenna gets snagged during a crash, the pulling force won't be transferred to the UFL connector. If you remove the insulation of your antenna for weight-saving reasons, make absolutely sure that the uninsulated part can never touch the board to avoid creating a short circuit. Everything takes practice, my Whoop friends. The following chapters of this video are meant to help you, inspire you, and motivate you to build your own antenna. The best way to start is to buy a few 5.8 GHz or 2.4 GHz antennas and practice with them. Don't expect everything to go perfectly the first time. Especially stripping the outer jacket and shortening the shielding takes a bit of practice. If you want to build simple, linearly polarized, omnidirectional monopole antennas, you can also buy linear polarized 2.4 GHz antennas and turn them into 5.8 GHz linear polarized antennas by shortening the active part. That's also possible with 2.4 GHz T-Style antennas, which you can modify into 5.8 GHz T-Style antennas.
If you are new to this channel, please also check out my other videos and tutorials. I have put a lot of work into some of them and would be happy if many people see the videos and get help. Because I don't have many videos of new products on my channel like other channels, I rely on your support in the form of likes, subscriptions and comments, my friends. In this way, my videos are still appreciated by the YouTube algorithm. And so I can continue to offer you independent advice from my extensive whoop race experience as well as my many years of model flying experience with 3D RC helicopters, scale RC helicopters and RC aerobatic airplanes and more. You can see part of it on my second German language YouTube channel. Thank you in advance, my whoop friends.